Okay, so we're finally going to talk about functions. So I told you, I think, on the first day of class that the theme of this course is function. Okay, functions. So we're finally there. We've done enough. We've done some review. We've done some prep work to understand the concept, and today we're going to talk about what a function is. So we spent several weeks looking at various mathematical models that describe the real world, relationships between quantities. Today we're going to study functions, and functions are used to describe a special kind of relationship between two variables. So for example, the cost to ship a rug from New Mexico to Greenfield is a function of the weight of the rug. Oh, sorry. Yeah. Okay, so the cost to ship a rug from New Mexico to Greenfield is a function of the weight of the rug, or it depends on the weight of the rug. So the two variables in the rug example, we call the cost the dependent variable because the cost is dependent on the weight. So we call the weight the independent variable. Okay, so I would like you to come up with two examples of a function. So two variables where one is dependent on the other, and write down, record which variable is dependent and which variable is independent. Okay, I saw lots of really good examples of functions. I had, I think, Corey, I saw you writing about a paycheck. So what is that a function of? Yeah. Yes. So your paycheck is a function of number of hours worked. So which one is independent and which one is dependent in this case? Paycheck is the dependent variable, because it depends on hours worked, which is independent. Okay. What example did you just give me? Oh, the rental car one, right? When you rent a car, the cost is dependent on how many miles you drive. Car rental cost is a function of number of miles driven. And the cost is dependent. Number of miles is independent. And then I saw another good one over at this table where your speed on a snowboard that's going downhill is a function of the slope of the hill. Right? The steeper it is, the faster you're going to go. So your speed on the snowboard is dependent, and the slope of the hill is the independent variable. Anybody else have an example they want to share? How much time has passed since you were born? Aren't they the same thing? Your age and the time that has passed since you were born? Yeah. Okay. So function is a special kind of relationship between two variables. It's a rule that assigns to each input one and only one output. So they describe a relationship between two quantities. Think of it like a machine or a processor. It takes in an input and it delivers an output. So you drop in an input, an X or a number or whatever, and out pops a output, and exactly one output. Okay, you don't drop something in and sometimes you get one thing and sometimes you get another. when you put in an x, you always get this thing, which we denote f of x. F parentheses x, we read f of x. So I always think of a couple of everyday things to help me remember what a function is. So for example, a television is a function machine. You input a number, right, the channel, and the output is what comes up on your screen. Okay. So if I input 22 into my television function machine, what's the output? 22? I'm assuming we all have the same. Springfield. that's our NBC affiliate, I believe. So if you put in 22, your output is NBC, right? So 22 NBC. And it's always NBC, right? You don't put in 22. Sometimes you get NBC and sometimes you get Lifetime, right? It's always exactly a one. For this input, there is exactly one output and only one output. Okay. Now, is it possible that I have two channels that are the same thing, two numbers that give me the same station? Yeah, they're like 50 ESPNs, right? So if I put in two different numbers that give me the same output, that's allowed. The machine still works, right? It still makes sense. But so I could have, 50 and 51, say, both give me ESPN. That's fine. I'm not going to call the cable company and be like, what's wrong with my TV? But the only time I would have a problem is if I put in, say, 17, and sometimes I get ABC, and sometimes I get, the Wii network, right? Then you're going to call the cable company and say there's a problem with this cable box, right? So a function machine can have two inputs that have the same output, but it can't have one input having two different outputs. Okay. So I always, because it's very confusing, like to just think of the wordy definition, which is each input has exactly one output, and an input can have, two inputs can have the same output, but you can't have an output that came from two different inputs. It gets very wordy, but if you remember this analogy, it'll help you remember what's allowed. So for this is not allowed. This is okay. So a function is a special kind of relationship between two variables where each input goes to exactly one output. So here are just some really familiar basic functions. Okay. Like I said, it's a relationship between two variables, so we can express that as an equation, or a table, or a graph. So if I have y1 is equal to x plus 2, I can make a list of inputs and outputs. Make a list of some x's, maybe I'll do -1, 0, 1, 2. And I could get the outputs. So if I plug in here, -1 plus 2 is 1, 2, 3, 4. Does that equation appear to be a function? Yeah, it seems like each x value, no matter what x I plug in, there's exactly one y is going to be the output. So this one's okay. And if I wanted to graph it, it would look like something like this. So y equals x plus 2. I just graphed the y-intercept of 2, and then I went up 1 over 1 because the slope is 1, drew another point, and connected them. Okay, y equals x squared plus 2. Let's try a few different x's here. If I plug in a -1, what do I get for y? 3. Great. And if I plug in a 0, I get 2. What if I plug in a 1? 3 again. And if I plug in a 2, I get 6. All right. Is this a function? Yes, yes. Each input is giving exactly one output, and it's okay to have two different inputs give the same output. That's allowed, right? So that's allowed. If I want to graph this, I could just plot my points and see what it starts to look like. 0, 2, 1, 3, 2, 6. And then if the points aren't enough, you could just plot some more points, or you could have your graphing calculator graph the equation to get a better idea of the shape. It looks something like this. So this was a yes, this was a yes. Okay, let's look at the absolute value of x. Plug in some different x's. If I plug in a -1, what do I get for y? 1. If I plug in a 0, I get 0, 1, and 2. Does this look like it's a function? Yeah. Yep. Each input is giving exactly one output. That's good. And it's okay for two different inputs to give the same output. That's allowed. Okay, so the absolute value of x looks like that. Just plot the points, connect them. You get that V shape. Okay, so can anybody think of an equation that would not be a function? Where you have one input that would give two different outputs? Square roots, yeah. So maybe if I did x equals y squared, right? Because then I'm going to have to square root to get y. So I do -1, 0, 1, 2 for my x's. Well, if I try to replace the x with a -1, what do I get for y? Right. Y would be undefined. There is no solution to that equation. So here I just put undefined. There's going to be no y value there. And if I replace x with a 0, I get 0 equals y squared. So y would have to be 0. Okay. And if I replace x with a 1, what do I get for y? Plus or minus 1. Two outputs. One input, +1, and I got two outputs, positive and -1. Okay. And then instead of doing 2, let's do 4. So if I do 4 equals y squared, then y would have to be plus or minus 2. So I'm getting more than one output for one input. So this is like, I'm putting in channel 4 and I'm getting two different stations, ABC and Lifetime or whatever. So the graph of this thing ends up looking like, let's see, 0, 0s on the graph. And then when x is 1, y could be +1 or -1. Okay, so when x is 1, y is +1 or -1. And when x is 4, y is +2 or -2. And we end up with a shape kind of like that, parabola on its side. So this is not a function, because for various inputs, right? Like for 4, for an input of 4, I had 2 different outputs. Not allowed. Okay, so it's important to remember that a function always has exactly one unique output for each input. So here are some different birthday functions. We're going to write down some inputs and outputs for a few people, and then we're going to see which of these two is a function and which is an imposter. So here's birthday function 1. The input is going to be a person's name, and the output is going to be that person's birthday. Okay, so if I put down me, my output would be 10, 7. Okay. Somebody, who else do we? Andrew, what's your birthday? 12/16. And what's your last name again? So A. S. Somebody else give me their birthday. 12/18, and that's Dan Cleary, right? Okay, so we get the idea, right? The input is going to be somebody's name, output is going to be their birthday. Is this a function? Hearing some contradictory answers here. So for any given name, how many birthdays can they have? Any given person can only have one birthday, right? People can have the same birthday, but that's allowed, right? So yeah, like let's just pretend that Maria's birthday, don't correct me if I'm wrong, okay? Maria's birthday, we're going to say, is also 12/16, right? This is still a function, right? Still a function. It's okay to have 2 inputs that give the same output, but there's no way I'm going to put in somebody's name and they're going to have 2 different birthdays. You can only have one birthday, okay? So this one is, yes, a function. Now for birthday function 2, the input is going to be a month and a day, and the output is the name of a person born on that day. So let's see, if I put down 10/7 as the input, the output could be me. Anybody else in this room have a birthday on October 7th? Okay. Is it possible that 2 people in this room could have the same birthday? So let's just make it up, right? In fact, we have 12/16, right? 12/16 is going to be my input, and my output would be both Andrew and Maria. Right. So is this a function? No. No, because it's possible for a birthday, for a given date, to have more than one person who has that birthday. So this one's a no. Okay, so this is just a little bit of reading, just to remind you of how some of the things that we talked about. You can read this later. And I have another packet for you. Okay, so an important thing to remember, f parentheses x is read f of x, and it means apply the rule f to whatever's in parentheses. Okay? It does not mean f times x. This is a very common mistake when you first learn about functions and the notation that it surrounds functions. It looks like f times x, but f is not, f is just the name of a rule. It's not a variable. Okay? So you can't actually multiply them. So we use letters f, g, and h to represent functions. They're not variables. They're the name of a rule. we call the input x, and we write the corresponding output as f parentheses x. So f of x is now the output. It's just a fancy way of what we used to write y. Okay, we used to write y, now we're writing f of x. So I have g of x equals x squared plus 3x. So think of g of x as an entire thing. It's just like a y. G of x is the output. So describe in words, what does this function do? When you drop something into this function machine g, what does it do to it? Squares it and adds 3 times it. So any input we put in, it's going to get squared. Whatever we put in is going to be squared. And then we're going to add 3 times it. So what would g of 3 be then? 18, yeah. So whatever I put into the g machine gets squared, and then 3 added to it 3 times it. So that's going to be 18. What about g of 0? What would that be? 0. Because I would do 0 squared plus 3 times 0, which is 0. How about g of t? If I drop a t into the g machine, what's g going to do to it? It's just going to square it and add 3 times it. Remember, g is just a machine. It can't think. Whatever you put in, it's just going to do this too. It's going to square it and add 3 times it. Doesn't matter if that thing you're dropping in makes sense to you or not. So we have 4 ways that we can represent a function. Verbally, I can explain to you in words what the function machine does. Yeah. Oh, are there? Did I miss them? Ah, look at that. G of t plus 2. Okay. So the g machine takes the input, squares it, and adds 3 times it, right? So here's my input, t plus 2. It's going to get squared, and then I'm going to add 3 times it. And we could do this out. This would be t squared plus 4t plus 4 plus 3t plus 6, which is t squared plus 7t plus 10. But you could have just left it like this too, doesn't matter. And then g of 2x. Okay, so the g machine takes whatever input you give it, squares it, and adds 3 times it. So my input that I've been given is a 2x. I'm going to square it and add 3 times it. What is 2x in parentheses squared equal? 4x squared. You got to square both parts there. And then 3 times 2x is 6x. So 4 ways to represent a function. Verbally, I can say to you in words what this particular function machine does. Right? The last one I said it squared it. It takes things and it squares them and adds 3 times it. I could give you an algebraic or symbolic formula for what it does. So in the last one we said f of x equals x squared plus 3x. That was a formula. We could make a table of values where you have an x, an input column and an output column, an x and a y, or an x and an f of x. Or I could make a graph where you have x and y, or x and input and output. Sometimes, yeah. So here's a function, and I want to represent it in all four ways. F of C is going to be the Fahrenheit temperature corresponding to a Celsius temperature C. So a verbal rule. To find the Fahrenheit equivalent of a Celsius temperature, what? I hope so, because I don't know. We subtract 32 and multiply by 5/9. And then multiply by 5/9 after you've subtracted 32?
Yes.
Okay. Okay, good. So when you do the verbal rule, you don't use any symbols. You just write out in words what's happening. So using the verbal rule, we could switch 10 degrees Celsius to Fahrenheit. So I would subtract 32 from it, right? So I would get negative 22. And then I would multiply that by 5/9. So that would be negative 110 over 9. -12.22 degrees Fahrenheit. Does that make sense? 10 degrees Celsius. What's freezing in Celsius? Right. What's freezing in Fahrenheit? 32. Okay, so 10 degrees Celsius, is that below or above freezing? Above. Negative 12 degrees Fahrenheit, below or above freezing? Below. So there's something wrong with this formula. Multiply by 5/9 first. Celsius to Fahrenheit. Add 32. Okay. Okay, so I take 10 and I add 32, I get 42, then multiply by 5/9. 9/5, okay. So we had the opposite direction.
Yeah.
Okay. Oops. Okay, 42 times 9/5. 75.6. Does that make sense? Let's just double check. Okay, so we had it wrong again. Third time's a charm, yep. So we're supposed to take the temperature in Celsius, multiply by 9/5, then add 32. Okay, so we take 10 degrees, we multiply by 9/5, then add 32. So 10 times 9/5 is 18. 18 plus 32 is 50 degrees Fahrenheit. Okay, very good. 9/5 and 1.8 are the same thing. Is that what you're asking? Oh, okay. Okay, so now I want to write an algebraic rule. In general, for a Celsius temperature C, I want to multiply it by 9/5, then add 32. So using the algebraic rule to find f of 10, I'm going to replace the c. This c in parentheses got replaced with a 10, so I have to replace all my c's with 10s. So f of 10 is going to be 9/5 times 10 plus 32, which is 50. Okay, so that's our algebraic representation. For a numerical representation, I would make a table of values where I list a bunch of Celsius temperatures and their equivalent Fahrenheit temperatures. So using the table, what's the Fahrenheit equivalent of 10 degrees Celsius? 50. Good. And then I can also represent this relationship graphically, where I put Celsius along the horizontal axis and Fahrenheit along the vertical axis. And using this graph, I can try to figure out what the equivalent is to 10 degrees Celsius. So I find 10 degrees Celsius along the Celsius axis, go up to the graph, and see that it matches with a 50 degrees Fahrenheit. Now, what do the dots in part D have to do with the table in part C? The dots on the graph, what do they have to do with the table? Simpler answer. They're the points, right? 10, 50 is a point on the graph. That's all. So each pair of Celsius Fahrenheit equivalencies make a point on the graph. Okay, so one last important topic for functions is domain and range. So the domain of a function f is the set of all possible input values for which the function is defined or makes sense. And the range is the set of all the possible output values. So I think of this, the domain is the set of all things that won't jam the machine. Like, if you tried to type into your television remote, 5,000, unless you have like some crazy cable package, what happens? Nothing, right? 5,000 is not part of the domain, right? The domain would be the list of all possible numbers you can type in. Okay, so or you think of it as like, if you actually think of it as a physical machine, something that you're going to drop into the machine, anything that won't make the machine jam or cause the machine to break down. Okay. And then the range is the set of all output values, set of all outputs. So the paper that you have that has a list of all the channels that you get, it says NBC, ABC, ESPN, all the channels that you get, all the list of outputs, that's going to be your range. All the things that your function machine can produce. So here's a function where my input is a person's name, and the output is the name of that person's biological mother. Is this rule a function? Why? How do you know? Right. Any person can only have one biological mother. So how do we know this is a function? Because any person has exactly one biological mother, right? So that makes it a function. What is the domain of this function? The set of all possible inputs. All people, right? All people. Because all people have a biological mother, right? So all people is the domain. What is the range of this function? What kind of outputs can we get? Only people who are biological mothers. So input, I can put in anyone, but my output is only biological mothers. So here's a graph of a function. Each input has exactly one output. You can pick any input you want, like pick 5, right? It's got one output. Okay, so it is definitely a function. Now I want to know its domain. What are all the x values for which this function exists? The whole thing is a function. The whole thing is one single function. It's just not connected. So let's just look at the first piece. Okay, ignore the curvy part. If you just look at this little line, what x values does that line exist for? 2 to 6. Good. Okay, here to here. So that's part of its domain. Okay. Now look at the curvy part. What x values does the curvy part exist for? 7 to, I guess, if we assume that goes down forever. Yeah. We could say 7 to infinity. So I just drew on the x-axis, I just highlighted the domain of the function. So my domain is going to be 2 to 6 unioned with 7 to infinity. Now let's look at the range. Okay. So the range is y values. Domain is x values, range is y values. So look at this little line again. Okay. What y values are represented by that line? 4 to 6 from here to here. And then look at the curvy part. What y values are represented? Two to negative infinity. Have I left anything out? Hint, yes. What? The peak, yeah. There are some y values that I haven't taken into account here, because the highest point on this graph is right here, and if I go over to the y-axis, there are several y values that I have left out. So it doesn't just go from 2 to negative infinity, it actually goes from like 2.5 or so to negative infinity. So my range is going to be negative infinity to 2.5. Unioned with 4 to 6. Now I'm using all square brackets because I just am assuming that these are all closed. Because the open circles were just a quirk of the graphing program that I was using. So fill those in. Okay, so we've got the domain and range. That's good. Okay, so sometimes a domain is given explicitly, as in this example. F of t is equal to negative 16t squared minus 48t. And then it tells you t goes from 0 to 4. That's a set of input values. And that's the, what? Thanks. Okay, so I want to estimate the following function values using my graph. Okay, so f of 3. 3 is what, an input or an output? An input. Anything that you see in parentheses there is an input. So that is an x value, and it's asking you for the y value. Okay, so I go up to my graph. Yep, so I go 1, 2, 3 is right here. I go up to the graph and see what my y value is. Looks like about 4.5. Okay, and then f of 15, same thing. I want to find a 15 input. So 15's right here. Go to the graph, and the output looks like it's about what? Almost -2, -1.8, something like that. It's approximate. So is this one. And f of 6.5. So I go up to my graph. I got to find a 6.5. That's right here. And then I found an x value. Now I have to go to the graph. Uh-oh. There's no graph at 6.5, right? So what do I say? Undefined. Great answer. Undefined, because 6.5 is not in the domain of the function. All right, and then I want to find values of x for which f of x equals 2. So now they're asking for x, so they're looking for an input, and they've given you the output of 2. So if I go up to my graph, I want to go to a y value of 2 and find the x value that will give that input, that will give that output. So if I go over to the graph, there's 1, right? That happens at 7. And then if I keep going, though, there's another one, and that happens at 11. So there's actually 2 x values, 2 inputs that give an output of 2, 7 and 11. Okay, so sometimes domains are just given to you, and you don't have to think about it at all. So for this example, they gave you an equation, and then they also gave you a restriction on the t values. Okay. The set of t values that you're allowed to plug into a function is the domain. So my domain here is 0 to 4, right? It's just that. They gave it to you. Here's another one where it's given explicitly. The American Medical Association says that the number of doctors, f of x, so the output is the number of doctors, in the private sector in year x, so x is the year, that's going to be your input, can be modeled by this equation. And they put in parentheses only for these years, right? This equation is good just for these years, so that's my domain, 1970 to 2000. They gave it to me right in the question. The set of inputs that this equation works for is just 1970 to 2000. Okay, other times domain is implied. It's not given to you outright. You have to just say what values of x make sense for this problem. So here's a function. What would be the domain of this function? What x values make sense? What x values are you allowed to plug in? 2 to infinity. Anything bigger than 2. Okay, because you just can't take the square root of a negative. So this is exactly the same as when we were finding domains of expressions a little earlier. It's just that now we're calling these expressions functions. They have a new name. What's the range of this function? What kind of outputs can we get? Yeah. All numbers? All real numbers? Can I get negative 10? What x should I plug in to get negative 10 as the output? You can't, why not? Right, the square root of a number is always positive, right? The square root of 9 is 3. Square root of 100 is 10, right? So the square root of anything is always positive. So this is just all real positive numbers, including 0. I can get 0 if I plug in a 2. So one way to help you, we kind of reasoned through that you can only get positive answers, but another thing that you can do is look at the graph. Oops. So I want to look at the graph of x square root of x minus 2. Just going to use a standard window. So in this picture, you can see the domain, 2 to infinity. And you can see the range, 0 to infinity. So let me just take a picture of this. Okay, so if I look at x values, so I look at the curve and I say, okay, well, it covers these x values going from 2 to infinity. And then I look at what y values it covers, and it goes from 0 up to infinity. So all positives, yep. No, the square root of 100 is just positive 10. It's a good question. So the square root definition says the positive number that when squared gives the result, right? So if I'm looking for the square root of 100, I'm looking for the positive number that when you square it, you get 100. So that would be positive 10. So it's actually in the definition of square root that the result is a positive number. The plus or minus only happens when we solve an equation like this. And I square root both sides, right? And it actually turns out the square root of 4 is 2. What's the square root of x squared? Nope. X or negative x. X or the opposite of x. Because, let's make a little table so you can see. So if I plug actually, let's do perfect squares. Okay, so if x is 3, the square root of x squared, so I would square the 3 and I get the 9, square rooted, I get the 3 back, right? If I plug a 2 in here for x, I would get, okay, well, 2 squared is 4, square rooted is 2. If I plug a 1 in here, I would say 1 squared is 1, square rooted is 1. But what if I plug in a negative 3? What's negative 3 squared? Positive 9, and the square root of 9 is 3. So I plugged in an x, and the square root of x squared was not the original x, right? It was the opposite of x, positive x. So the square root of x squared is actually the absolute value of x. So if I plugged in a negative 4 here, I would get the positive 4, right? When I square root negative 4 squared, I get the absolute value of negative 4. I get the positive number back. And then we just learned how to solve absolute value equations, right? And it says that x has to be 2 or x is negative 2. So the plus or minus that pops up when you're solving that equation is not because of the square root. It's because when you square root x squared, you actually get an absolute value. And we often don't write this down. It's just we jump right from here to here as a shortcut. It was a good question. Thank you. Okay, last little thing. Hopefully we'll finish up. Remember, a function has exactly one output for each input, so is this graph a function? No, there are lots of places where, say at 4, I have 2 different outputs. 2 y values for a single x value, not okay. You can only have, each x value can only have one y value associated with it. Right, you can only have one output. This one has multiple. So we use that fact to create this little shortcut called the vertical line test. If any vertical line intersects a graph more than once, then the graph is not a function. Okay. So which of these graphs is a function? This one, if I sweep a vertical line through it, does it ever touch more than once? Oh, so that one's okay. How about this one? Vertical line. Okay. How about this one? If I sweep a vertical line through, nope. Circle, nope. That touches in 2 places. There's a vertical line, touches in 2 places. How about this one? No, because there's one spot. If I draw a vertical line right here, it's going to touch in 2 places. How about this one? Yeah, this one's okay because I uncolored this dot down here. So now if I draw a vertical line there, it only touches one piece of the graph. So that one's okay. Because it's not filled in, right? Okay, that's it. Hand in your project on your way out. You're going to have to look at this activity on your own.